been destroyed, you see that. And 1/2, well, you can't, that's really pretty rational, okay? You saw that this one survived. It survived despite putting in a perturbation of 0.2. The bigger the perturbation, the less of them survive. Let's show that. Let's go back to the program. Option return. Let us put in a perturbation here of size 0.3. So right away you can see those points. Remember I was saying things are going all over the place? I said you couldn't cross one of those curves? The curves that survived? Well, I don't think anything survived. Well, possibly there's a curve down here. I'm not sure. But you can see these points are not being blocked by anything. All those curves have died. They've all been destroyed by the perturbation. We could play around with, just because it's not blocked. We can play around between 0.2, 0.3 and see when this happens. Let's see. Change initial conditions. Let me see. Let me go in one of these things and see what happens. There are islands. There are no more curves, but there do seem to be islands here. We see 3, and we see a 5 here. Or is that a 4? 1, 2, 3, 4. Yeah, a 4. An island of 4 over here. And of course we see 1 and 2 over here. We see it's very big. But you see there are no more curves that separate, that those blue points, they got you everywhere. No more barriers. Now we can do, as I said, a calculation. The one calculation that we'll do, option enter, that will tell us about this, Km here. What Km said is, if the perturbation is sufficiently small, then some very irrational ones survive. And now we have to say what we mean by very irrational. A torus whose velocity is close to a rational with a small denominator is destroyed by a small perturbation. A torus whose speed is sufficiently far from all rationals, then it is called very irrational. It requires a large perturbation to be destroyed. The most irrational number is the golden mean. It is the furthest from any rational. We'll see what that means in just a second. And that torus is the last one destroyed. If we were to measure, if we were to look at those lines, if we had picked out one that had this golden mean as velocity, it would still be there when most of them were gone. Okay, so let's do a calculation that I think will make this clearer. Here is what the Km theorem says. It says, let's talk math language, but we'll make it clearer. It says there exists a function k of epsilon, which tends to 0 with epsilon, such that if omega satisfies, omega is a distance greater than k over n to the 5/2 from mn for all mn, then the torus with this winding number, omega, survives a perturbation of size epsilon. So let's see, what does this mean? This is basically digging out intervals around here's a fraction, mn. So here's an mn, m over n. We make to the right and left an interval of size k over n to the 5/2. So for a big denominator, if n is big, my interval is small. For a small denominator, it's big, right? So around each fraction, I'm making a little interval. So you can imagine, you'll just have to believe it, but you'll see from the calculation. You take all the rationals, and you make little intervals around each one. Now you're going to say, you make little intervals around each rational, of course you're going to fill up the line. There's nothing left. But that's not true. A lot of those rationals have very big denominators, and you're making very little intervals around them. And it turns out there is something left. Right? If, as you If you took all the rationals and you made an interval of the same size, then yes, of course you would fill up the line. But if for rationals that are like 132 over 1,955, you have a teeny tiny interval, it turns out that you can do that and have something left over. That's what KN says. And let us do the okay, so this is what he says. And we will just, let's do the calculation. Let us estimate the measure of interval, how many of them, what's the size of what's the measure of velocities of surviving torque. So we're going to do a calculation for all rationals. How are we going to do that? Well, we take a sum over all the denominators. How many fractions are there with denominator n? Well, there are n minus 1 of them. Okay, so we're going to take n for each n. We're going to have n such intervals. We're talking about the interval between mn minus this left bound to mn plus the bound. So what's the size of this? It's twice the radius, 2k over n to the 5/2. How many such fractions do we have? Well, m varies from 1 to n minus 1, so we have n of them. In fact, we have n minus 1 of them, I guess, but let's say we have n of them, we're going to count 0. Okay? We have n such fractions, the denominator n. Everybody agree with that? We're measuring an interval of size of radius k over n to the 5/2, of diameter 2k over n to the 5/2. So now we do that sum, n over n to the 5/2 gives you n to the 3/2, and of course this power isn't chosen by chance. It turns out this sum, despite being infinite, has a finite result. You've seen such things before, you know that can be. You can check it with you can estimate it with an integral. You integrate 1 over x to the 3/2, even up to infinity, you get x, this is x to the minus 3/2, its integral is x to the minus 1/2, right? And you get 2/3 here. And so that gives you the integral actually is finite, and you get 4 times k over 3. And you recall that this the theorem says that, of course, this k of epsilon goes to 0 as epsilon over 0. Epsilon goes to 0. Why is that? This epsilon is supposed to be the size of the perturbation, and naturally, when the perturbation goes to 0, well, everybody survives. This k is this radius around the perturbation of size epsilon is destroying is digging around each rational something of size k over epsilon, over n to the 5/2. It's digging out these, by digging them out, I mean the picture, I meant the picture before. Digging out means, anyway, the picture before, there are these curves, there's another curve, and in between there are those islands. That's what's being dug out. It's being dug out around each rational. And for rationals that have small denominators, something big is being dug out. We saw that. We saw that the 2 chain was really wide, and the 3 chain was kind of smaller, and the 4th one was smaller still, and the 5 one was really small. Right? We saw that? We can go back to, see, not that. So that's what k is. It's the radius. K over n to the 5/2 is the radius of what's being dug out. And of course, if the perturbation is 0, there is no perturbation, nothing is dug out. Hence k this requirement that k goes to 0 as epsilon goes to 0. Anyway, since k goes to 0 as epsilon goes to 0, you can see that all we need is k smaller than 3/4. Right? We can pick an epsilon such that k is smaller than 3/4, since k goes to 0. 3/4 is not very close to 0. And then we will have some, this thing will be less than 1, and some of them will be left. Some of them will be left. So this is, okay, again, this is not a proof, this is a statement here that there exists such k. But it's showing how the theorem works. It says that these are the regions that have been destroyed, and there's some that's left. And I guess maybe we'll go back to the picture, and we'll see. this picture again. Doesn't take very long. So 1/2 has been destroyed, as has things that are close to 1/2. It's not just 1/2 that's been destroyed. Things that are close to 1/2 have been destroyed by this perturbation. But here's one that hasn't been destroyed. This is still a curve. And its velocity is sufficiently far, or its velocity is sufficiently far from any rational that it's part of what's not been destroyed. No points cross that curve. Anyway, so we saw this before. This is now what's been destroyed around 5, around the velocity of 5th. That's pretty rational, but still not as rational as 1/2, meaning that its denominator is bigger. Okay, so you see curves. You see that there's still barriers. Okay, so that's a large part of what I wanted to say. Option term there. There's a few more things we can say, but let's see, which one is it? 2. Okay, we can talk about the two-body problem. The two-body, because after all, Hamiltonian mechanics was made for celestial mechanics. So the two-body problem, we set it up in this way. We have a big mass, big M, and we have a little mass, mu. Little mass, mu. And it has the little mass, we're looking at the position and velocity of the little mass. It has position in r phi, and it has momentum, radial and angular momentum. Okay? Its Hamiltonian is its momentum squared over twice the mass plus the potential energy. Okay? Potential energy, the gravitational energy between the big and the little. The mass, the momentum we write is PR squared plus P phi squared over R squared. And it's a Hamiltonian system. We write dr dt is dh naught dpr, and that gives us, we can take this derivative, we get 2pr over 2 mu, meaning pr over mu. We get dpr over dt, that's minus dh naught dr, the position, the radial position. So we take the derivative of this with respect to r, and so we get from r to the minus 2, we get r to the minus 3, with a minus sign, minus 3 here. And then we have the derivative from minus 1 over r, we get 1 over r squared with a minus sign, so it's minus 1 over r squared. So this is dpr dt. dp phi dt, well, this thing does not depend on phi, and hence this is conserved. And d phi dt is p phi mu r squared. This has 2 degrees of freedom, and we have found another conserved quantity, which is the angular momentum. And hence, this is an integrable system. Remember, h is always conserved. H naught is by construction, by definition, by whatever you want. And we have another conserved quantity, and hence this is an integrable system. Okay, no chaos. Now, what about the three-body problem? I think everybody knows, I think it's true, isn't it? The three-body problem in general is not solved. I mean, people thought it would be, and this was a big part of what occupied mathematicians and physicists in around 1900. There were big prizes given for solving it, and Poincaré gave solutions or partial solutions, and anybody did, and people found partial results, but there was no general solution or theory for the three-body problem. There are a bunch of special ones, and here I'm about to talk about one of the special theories, the restricted three-body problem. So here are among many people, the circular restricted three-body problem. The hypotheses. We have a very big mass, like the one we were just looking at, a very little mass, like the one we were just looking at, and a medium mass. Okay. So this could be like the sun and an asteroid, and this is the moon. Or maybe this is Jupiter or something. This is some perturbation. Mostly this is the sun, and this is, so are there some examples given? Yeah, a planet and an asteroid. So the hypotheses. Mu moves under the influence of big M. That's the integrable part. And then there's a non-integrable perturbation that comes in when you have this perturbing planet. Mu is sufficiently small that we neglect the effect that mu has on little m and big M. And we identify the center of mass of the system of the M, and this is supposed to be green, this M here, this system with the mass of big M. And we assume that little m here, the green M, has a circular orbit, and that everybody remains in one plane. And the plane contains, of course, big M and little m are in plane. Find them, but little mu didn't have to stay in that plane, but we restrict ourselves to that. So those are the assumptions of the circular restricted three-body problem. So we have the integrable system. This is what we talked about just before. We did all this just before, and we had that dphi dt, dp dt was conserved. These are the equations that we just did. Okay, everybody agree with that? This says it's conserved. This is now without the green M. We're now going to add on the green M. Here we are. Here we've added on the green M. This is now a new Hamiltonian, and this is a non-integrable perturbation. And why is that? Rm of t changes its orientation. H now is non-autonomous. It depends on time. We still have only the p phi that's conserved, but we have an extra degree of freedom, and that's not enough. Now we can change this to be an autonomous system by going to a rotating frame. So we're going to change our frame such that we always have Rm in the same place. We're going to have a phi prime that moves with angular velocity omega. But we'll retain the definition of p phi. Okay, in that case, since phi prime is phi minus omega t, we need to find our new h prime. H prime is such that dh prime dp phi is d phi prime dt. We know what phi prime is. We're trying to find what dh prime is. D phi prime is d phi dt minus omega. We remember that d phi dt, it's over here, is p phi over mu r squared. So this is an equation that we have for h prime. So we used to have h naught prime here, and this is it in a rotating frame where we put on the minus omega p phi. Now, when we put in the new one, we have gm mu q minus rm. But this doesn't change. Rm is constant. This is the Coriolis term. We then can make an action variable, which is p phi, and another one, I phi, which is p phi, and another one, ir. This is for the unperturbed system. And we find those action variables, we find, remember that we're finding i's that are conserved. We now find two frequencies, dh naught dir and dh naught di phi. And we find that they differ by omega. So we have two frequencies. And so now we're almost finished. We go back to what we said before about the billiards. We were talking before about rational versus irrational velocities. What does that mean, rational? What if we measured in units of pi? That would turn everything that was rational into something irrational, right? So what does that mean to be rational, irrational? The only thing that can make sense is if we're talking about ratios. And before that means that we had a time that was going on. We had a time, we go here, we go here, we go here, we go here, we go here. We had a unit of time. Now, in this problem, what we're going to be concerned with is these two frequencies here. And the question is their ratio. Is their ratio rational? That's what we're going to have. One of them is keeping time, just as before, we kept time as we went around. And the other one is going to be the perturbation. So we have these two frequencies. We look at their ratio, which is the only thing that makes sense. And we find, excuse me, and we apply this KM theory. That is to say, this mu was happily doing an orbit around big M if green medium M had not appeared. But now green medium M, it perturbed it. It's a non-integrable perturbation. And the question is our orbit broken or not? And that's the KM theory. And it's thought, so gaps appear. There are not allowed certain orbits, just as there weren't for those billiards. They're broken. Nobody can be there. And some people think that this explains the Kirkwood gaps. There are no asteroids found here. And what is here? This is positions. Positions, you know, we remember in celestial mechanics, positions go with velocities. When you're at a certain distance, you're going at a certain velocity, right? So these correspond to rationals that are 3 to 1, rational ratios, 3 to 1, 5 to 2, 7 to 3, 2 to 1. And there are no asteroids found there. And this is all from analyzing the orbital resonances with Jupiter. That's to say, taking big M to be the sun and taking that green M to be Jupiter. So we find here these rational places. The rational places are broken. They're the places where you no longer have those curves that you're going to cross. They're like the 1/2 and the 1/3. Some people, okay, I read this someplace. I don't know anything myself about celestial mechanics. Maybe some people think this is nonsense, and some people, at least at one time, thought it was true. I don't know if this is the explanation of the Kirkwood gas. In fact, maybe we could look that up right now. And I think that's all I have to say to you today. There's other stuff, but you'll see lots of things. Let's just look up the Kirkwood gaps. Let's see what people say about that right now. Kirkwood gaps are real. That is not a theory. There's a place where there aren't. Astronomy 104, homework number 6, solutions. So now you don't have to do your homework if you're in Astronomy 104 because the solutions are right here. So, okay, this from 2000 says that Kirkwood gaps are caused by the gravitational interaction between Jupiter and asteroids with these periods. Let's see. Wikipedia has perhaps been, let's see. Can people see? Yeah, more or less. Kirkwood gap is a gap in the distribution of the center of major axis or of the orbital periods of the orbits of main belt asteroids. So certain periods cannot be found because you're doing all that chaotic thing. You do not find an asteroid that just goes around. Gaps were first noticed in 1866. Who correctly explained their origin, the orbital resonances of Jupiter. So wait a minute. So is it definitely thought to be the case then? I thought it was just a theory, and I read that some people thought it wasn't the case. Perhaps.
My understanding was that it's more commonly accepted.
Oh, you think so? Oh, okay, good. I'm glad to hear that. Good. So, yeah, so good. So we've done billiards, we've done the Kirkwood gaps, and there, that's the end of this class. And thank you for coming an extra time. And I'll see some of you tomorrow.